I'm Dr. T. Welcome to my office. So today I'd like to talk about systematic error and how in the lab we design experiments to avoid it or at least know that it's there. Okay, so what is systematic error? This is when you measure something and your measurement gives you a number, and that number is always higher or always lower than what the true value is. So, you imagine how long something is. There's the true answer, and then there's how long you actually measure it. Now, we need to compare my value, the one I get in the experiment, to the true value. This is what we call accuracy. Accuracy is how close you are to the actual true value. Or I should say how close your average is, because you can average it, you got random error, let's get rid of that, do an average. But how close am I to that true value? I got a small problem though. If I am measuring something, I probably don't know what that true value is. Otherwise, why am I measuring it? Why am I doing this if I know what the answer is already? So what I need to do is I need a couple of tools to come in to help me figure this out. And what I'm looking for are standards and controls. Now, standards, I don't mean moral principles, which you need those too, but standards are going to be things that are just like your sample, or as close to your sample as possible, that you know what the true value is. So if you're measuring lead content in water, then you've got water with lead in it. And you know how much lead is in that water. That's your standards. So now you do your experiment on the standards. You then use that information to calibrate your experiment. So now, okay, I do this on my standards. I get these data. I can then use that data to modify my experiment so that then I can get the correct value for my unknown, the thing I'm really measuring. And usually this is an integral part of the experiment, because quite often you're not actually looking for the lead content of water. You're looking for how does the lead affect light and other things. So it's this kind of indirect step where you need to have an equation that tells, hey, how much the light was absorbed equates to how much lead. And that's where your standards are going to come into. So your standards are going to do that, and then it's also going to allow you to know that, yes, this number is accurate. Or at least hopefully. But you also need another set of chemicals known as controls. Controls are very close cousins to standards. So controls are going to be things where, once again, you know what's going on. They're virtually the same as your sample, but they're missing key components to it. And the reason they're missing key components to it is you want to know how your experiment responds in the presence of the stuff that's in your sample. What we call the matrix quite often. So if you've got, say, blood and you're measuring iron, the iron is your analyte, the thing you're testing, and the rest of the junk in the blood is your matrix. And blood, by the way, is a horrible thing to test. There is so much stuff in there, it's ridiculous. So what you want to do is you want to start looking and saying, like, okay, is something in what I'm doing going to create issues for me? Is there any reason why my standards and my samples might be a bit different? And if they could be, I want to make sure that that difference doesn't affect me. So typically what I want to do is run a negative control. Sometimes we call this a blank, because if you're working with spectroscopy, this is usually what you put in the instrument to start with to tell the instrument this is 0. So you run a negative control, and this is one where your experiment should find nothing. It should come out empty. And typically you might run a positive control. This, once again, could easily be one of your standards. So things can do double duty, and quite often your standards are your controls as well, depending on how it's set up. And so you got a positive control that you know the thing is there. Does your experiment detect it? So that way, you know that your experiment is working and it is picking up something accurate. If you look at a pregnancy test, you'll notice how they are. 1 line means you're not pregnant, 2 lines means you are. Well, the reason that second line exists, you could in theory just have the 1 line that tells you whether or not you're pregnant. The second line tells you whether or not the test worked. So you've got a whole bunch of chemicals all crammed into that part of the stick, And if they are able to make one line, then at least most everything, and really the whole thing worked. But if they can't make any lines, then you know that the thing didn't work. That way you know that it didn't work, not that you're not pregnant kind of scenario. Also, once again, you would all set up one where you're expecting it not to show up and hope it doesn't. A friend of mine, back when I was in grad school, we worked in the same lab. She was working with catechins, which are chemicals found in a lot of plant products, tea, wine, beer, anything with lots of ground up plant. And she was doing a cell viability assay. She wanted to know, well, did the cells die kind of scenario. And so she had a well that she was working in. So she had a plate that had lots of little tiny wells that you put the chemicals in, so kind of like miniature test tubes. And she had a well that had no cells in it. So when she did a cell viability assay, it was supposed to come back negative. It's supposed to show that there are no viable cells in it because it's sterile. What it had was it had the catechins, it had the buffers, it had all the other chemicals, but it never had any cells in it. And it comes back that it had viable cells in it. Wait, what? It can't have viable cells in it. It doesn't have any cells in it, period. And what we were discovering with this, and what she found out, was that the catechins she was working with, trying understanding how they affected the life of cells, were actually mimicking the cells in the cell viability assay, and thus her entire assay was not really measuring what she thought she was measuring. And thus she had to switch to another assay, and boy, the data looked completely different when she actually switched to an assay that was measuring what she thought she was measuring. So this is one of the core reasons of control. So you want to make sure that your experiment is actually testing what it is supposed to be testing. If not, you need to fix it or get a new one. And that's what my friend had done. So yeah, when you're setting up experiments, you definitely start wanting to make sure you've got part of your experiment set up that basically has everything but the one thing you're testing. That way you can make sure it shows up it's not there. You also want to have something where you know how much it is, so that you can know if the experiment works. And you might have several scenarios like this. So sometimes you need more than one or two controls. And then you always want to have some kind of standard where you know the value, especially if you're going for a quality or a quantitative measurement, that's getting a number, where you're able to say, okay, I know the concentration is this because this is what I set this other thing up to be. Now, some of this might actually be done, kind of by the manufacturer of your equipment. So, if you buy a ruler, they are comparing that ruler to standards provided by the National Institutes of Standards and Technology, or whatever organization, depending if it was made overseas, whatever organization that would have been governing that country's manufacturer of rulers. So some of these standards have already been done for you by the manufacturer of your equipment. But quite often, especially if you're doing you're making it yourself, you're going to need to make sure you have standards to know how to calibrate your experiment, how to detect an error that is constantly adding in or constantly subtracting from, as well as making sure your experiment is really, truly testing what you think it is testing. So with that said, happy experimenting, and see you next video.